Okay, good afternoon everyone. My name's Brian Tarrant, I'm the editor of Significance magazine, and it's my great pleasure to introduce the final session of RSS conference. That's if you discount the drinking and eating and dancing later on. Our speaker today is Roberto Trotta. He's a reader in Astrophysics at Imperial College London, where he studies dark matter, dark energy, and the Big Bang. Now, these are all deeply fascinating and exciting topics, and as a space buff myself, I was delighted to learn that there was a whole field of statistics, astrostatistics, that's dedicated to this important area of study. Now, unfortunately, my enthusiasm for the subject is not matched by my expertise, so I've tried going to astrostatistics sessions at past conferences, and I don't mind admitting that usually about 5 minutes in, I start to lose the thread and end up having to give up, I'm afraid. So it was fortunate that a few years ago now, I was introduced to Roberto by the late Joseph Hilby, who was the founding president of the International Astrostatistics Association. And Joe told me about Roberto's book, which is called The Edge of the Sky, All You Need to Know About the All There Is. And that seeks to explain the universe using only the 1,000 most common words in the English language. So I thought, now there's a man that could probably explain this topic to me. So Roberto was born and grew up in the Italian-speaking part of Switzerland. After obtaining a master's in physics from ETH Zurich and a PhD in theoretical physics from the University of Geneva, he moved to Oxford, where he was the Lockyer Fellow of the Royal Astronomical Society at Oxford University and a Junior Fellow of St Anne's before being appointed at Imperial in 2008. In addition to his research work, Roberto is an STFC Public Engagement Fellow and is the recipient of numerous awards for his research, teaching and science communication activities. This includes the Lord Kelvin Award of the British Association for the Advancement of Science, the Michelson Prize of Case Western Reserve University, and an Imperial College President's Award for Excellence in Teaching. He's also an elected Fellow of the International Astrostatistics Association. So his talk today will explain the role of astrostatistics, the role it's played, and how it will continue in helping answer some of the most fundamental questions about the physical reality of the cosmos. So please welcome Roberto Trotta.
Thank you, Brian. Thank you very much, and thank you to the organizers for having me here, concluding this fascinating conference. And thank you all for being here today. I promise I will use rather more than the most common 1,000 words in English tonight. Also because, after 10 years in this country, whenever I say that I've written a book using the most common 1,000 words in English, people are not impressed to learn that I've only managed to master 100 words a year on average. So tonight I'll use a few more. And so this is a summary of our knowledge of the universe around the 16th century or so, a summary that shows the Earth at the center of the universe here, surrounded by the 5 classic planets, the ones that have been known since antiquity, and the Sun, of course, going around the Earth, and the Moon going around the Earth as well, and then the fixed stars all around it. And so it took the Galilean revolution in the 1600s to wipe this model, the geocentric model of the universe away, and replace it with a model where the Sun is at the center of the solar system, and we are but one of the 8 or 9 planets, if you count Pluto, that go around the Sun. And when we moved forward with our knowledge, and at the beginning of the last century, we realized that actually our position is nothing special. We're but one of about 100 billion stars inside the Milky Way, our galaxy. And so we are not really that special. We're certainly not at the center of the universe. We're not at the center of the galaxy. And indeed, our place in the universe has been continuously demoted as our knowledge of the universe expanded. But if we fast forward to the present time, our place in the universe and our understanding of it is even more contingent now on our understanding of what's out there and how we can manipulate, understand, interpret the vast amount of data that we are gathering thanks to a wealth of satellites and telescopes. Here's a familiar picture, the Moon to scale. What I want you to focus your attention on is not the Moon, it's the little yellow square in this picture. Which, I put the Moon there to show you how small that square is. But if you now look at this little rectangle with the most powerful telescope that we have, the Hubble Space Telescope, this is what you see. There are 5,500 galaxies inside that square, and that square is so small that it would fit inside the eye of a needle held at arm's length. And each one of those galaxies contains about a few 100 billion stars, just like the sun. Now you do the maths, you multiply by the sky surface, there are about 50 billion galaxies in the visible universe alone. And that's the frontier of astrostatistics. That's cosmology. That's the kind of problems, questions, data analytic issues that I want to discuss tonight. What is even more shocking, if you haven't heard, is that everything that you saw in this picture is a tiny bit of everything there is. In fact, 96% of the universe is dark. It doesn't even show up in that picture. And that is one of the hottest research questions in the whole of science. What is the universe made of? What is the 96% of the universe that doesn't show up on that picture? Dark matter, dark energy. And as we shall see, statistics has a vital role to play in our quest for understanding this dark sector of the universe. And indeed, we now have a data that come to us from the far reaches of the universe. Here's a diagrammatic picture summarizing our understanding of how the universe came about in a phenomenon that we call the Big Bang, what we call time zero. Now here we sit 13.7 billion years later with observations ranging all the way back, almost to the very beginning. We have data from the very first light from the Big Bang, light that was emitted a mere 380,000 years after the Big Bang. Literally, the end of the visible universe has been mapped in great detail, as I'll show you later. We have data on the galaxy distribution in the sky in the intervening time, and all of this data point to a picture in which the universe started off in the Big Bang. It inflated exponentially in the first 10 to the minus 32 seconds after the Big Bang, and then it started to decelerate in its expansion under the presence of radiation in the universe, then matter in the intermediate phase of the life of the universe, mostly dark matter. But now, in the last 6 or so billion years, the universe's expansion has picked up pace. We believe now the universe is accelerating once again in its expansion, something that we cannot describe or understand using any normal form of matter or energy, and that led to the postulation of a new form of energy that we call dark energy, which is one of the biggest mysteries in physics today. And all of this is contingent on a great amount of data. I'm going to give you some examples, and on statistical techniques that we've used to interpret, understand those data, which altogether have led to our current status of affairs, where we understand that most of the universe is actually dark. There's a dark side to the universe that we really need to understand. So today I want to tell you a little bit about how we came to this state, observational cosmology, some history, and then give you a few examples of how astrostatistics has been absolutely fundamental, crucial in achieving those fundamental discoveries. I have a few examples here. Some of them I left perhaps for the Q&A or indeed for later. I am very aware that I'm the last thing standing between you and the final conference dinner and the partying, so I'll try to stick to my time here. And then at the end, I'll give you the big picture. Where is this going and why astrostatistics is going to be playing an even more fundamental role in the years to come. So astrostatistics, here's a summary of what astrostatistics is, really collaboration between astrophysicists here and a whole lot of statisticians, which are more often than not tend to look rather puzzled whenever we start flinging at them our jargon, and it takes a little bit before we can develop a common lingo to understand each other, really. Language is a big problem, understanding what we mean and putting it in terms that statisticians can work with. But when that happens, it can be really, really fruitful. And indeed, it wasn't always so that statistics and physics were two very different domains. And many of the advances, both in conceptual and computational terms in the past 2 centuries, have been due to either physicists or people working, mathematicians, working on physics and oftentimes astronomy-related problems. So for example, the method of averages introduced by Laplace was motivated by an astronomy problem he was working on. So was the least square regression by Legendre. Normal error theory is due to Gauss, and Bayes' theorem rediscovered by Laplace. And of course, Bayes' theorem should really be called Laplace theorem because Bayes didn't really do anything with it. Again, motivated by astronomy. And Bayesian model selection, something that astronomers have been using a lot of. And then on the computational front, many of the computational methods that are now ubiquitous have been discovered or rediscovered or popularized by physicists. But one thing that you will notice in this partial list of physics contributions to statistics and computational methods is that there is a big gap at the beginning of the 20th century. And that's clearly the moment in time where classic statistics was being born, and the likes of Fisher and Pearson and all the rest of it were really setting the foundations of what then became to be statistics as a branch of mathematics rather than as applied statistics or physics. And so the question is, what were the physicists doing, and particularly the astronomers, at the beginning of the 20th century? Why did statistics take the turn that it did, and it didn't continue on this quite impressive line that it was heading to in terms of astronomy problems and the likes? And the answer is that the astronomers were busy doing other things that didn't really need statistics. Actually, they did not need advanced statistics yet. Here is one great example of that. This is Edwin Hubble with a 200-inch Mount Palomar telescope in 1929. And what he was doing with what was at the time the biggest telescope on Earth was measuring the distance of objects that at the time were called nebulae. Now we know those are extragalactic objects, galaxies, away from the Milky Way. So we measured the distance of those objects from us and measured the velocity at which those objects appear to be moving away from us, the so-called recession velocity. And here are his original data. And notice there are no error bars on those data. Great tradition of physicists just putting in points. And then he did something that no undergraduate student would be allowed to do nowadays in the physics department, or indeed in the statistics department. He drew a straight line through this data set. And he said that the velocity was proportional to the distance with a proportionality constant that to this date is called Hubble constant. And indeed, it determined the value of this constant to be around 500 in appropriate units. The units don't matter to the discussion. We now know that it was widely off. This is the modern value of the Hubble constant and the error bar on it, about an order of magnitude off. But the point is that even though Hubble was wrong in the magnitude of the effect, and certainly from a statistical point of view it's debatable whether you could really infer a linear relationship given this data set, he was right in one fundamental aspect, namely that indeed distant objects in the universe are moving away from us faster than nearby ones on large enough scales. Which, if you think about it from the physics point of view, has the rather impressive conclusion, leads to the impressive conclusion that the universe is expanding. Hubble had discovered the expansion of the universe, and we can understand this with a simple metaphor that you can prepare in your kitchen when you put together a focaccia or a pizza dough next time. And this works actually pretty well. Those are olives here representing galaxies. The black olive is our galaxy, the Milky Way, and there is also a little French bean here that does nothing but gives you a measuring stick. As time goes by, the universe, as I said, the focaccia bread expands. And I did from the point of view of this olive, of course, our olive, that's to say, all olives are moving away from us, but if you look at it from this olive, all olives are moving away from that too. So you can see that the expansion of the universe is isotropic, is homogeneous, it's the same everywhere in the universe, and furthermore, an olive that's here, by the time we are here, has moved away by a larger amount from us because the pizza dough has expanded more between us and that olive. So that's the Hubble law in your kitchen, and then you put it in the oven at 200 degrees for an hour or a little bit less, and you get a fantastic focaccia that you can share with your friends. And so nowadays, with modern data sets, we have extended this data vastly. This is the domain that Hubble probed, and those are the modern version of his observations. And we have a fit here, a line, I'll discuss it more later, that is no longer just a simple linear fit. And here's the residual of the model to the data, and this is one of the key pieces of evidence that has led to us believing that the universe is actually accelerating presently in its expansion, and it is not slowing down under the influence of gravity as we would expect, and therefore lead to the conclusion that there is something out there that we don't understand, dark energy. Another pillar of cosmology, which didn't take off as a proper science until the 60s or the 70s, is the serendipitous discovery in 1965 by two guys working at Bell Labs of the relic radiation of the Big Bang, the afterglow of the Big Bang, the very light emitted by the Big Bang itself that had been cooled down and reduced in energy by the expansion of the universe in the intervening 13.7 billion years, and was being picked up by this microwave antenna by these two guys who are trying to communicate across the curvature of the Earth using passing satellites, an early example of satellite telecommunication, but could not get the receiver to work because they kept picking up a black body static noise that was continually interfering with the measurements they were seeking to make. They had no idea that what they had discovered was in reality the relic radiation, the leftover heat from the Big Bang that in the intervening time had cooled down to a mere 3 Kelvin, that's minus 269 degrees centigrade, and was filling the entire universe. And it was then Princeton team of scientists who had to tell them, look, this is what you have actually discovered. And those guys who made the discovery, they got the Nobel Prize for Physics, and the other guys who knew what this was and were trying actually to measure it, but didn't get there in time, got absolutely nothing. Such is science, but this is a fantastic discovery that really gave, settled once and for all the debate that had been raging in the 50s and 60s. Is it a steady state universe? It is being created as it goes along, or did it start in a primordial fireball, what Fred Hoyle, in a derisory fashion, called the Big Bang, a name that actually stuck. 1996, the COBE satellite measured the energy distribution of that light. And this is the measurement. The data points are here. The line is a one-parameter black body radiation fit, where the only free parameter is the temperature. The error bars, yes, I don't know if you can see it from the back, those are 400 sigma error bars. So I dare you to give me another example of physical sciences, or any science really, where you can plot 400 sigma error bars. The radiometer on board of the satellite had to be shut down 11 minutes after it got into operation, simply because they had reached the precision limit of the calibrating black body they had on board. This is the most precise oven ever produced everywhere in the universe, and it's been produced by the Big Bang itself. So this is proof that the Big Bang was a hot oven, effectively, at the level of precision that it beats anything we can measure. Again, another Nobel Prize for Physics in the early 2000s. But there was another instrument on board of this satellite that tried to measure not just the energy distribution of the radiation, it tried to measure the dependency of the temperature with direction in the sky. And so if you look close enough, that radiation comes from everywhere around us, because the Big Bang happened everywhere in the universe, but it's not quite the same everywhere around us. In fact, if you look with the precision of 1 part in 100,000, you start seeing tiny fluctuations, tiny temperature differences in the black body radiation coming from the Big Bang. And those temperature differences ultimately come from quantum fluctuations in the very primordial universe, 10 to the minus 43 seconds after the Big Bang. And they are very, very important to us, because it's out of these fluctuations that galaxies condensed out. And therefore, ultimately, those are the seeds out of which all galaxies that we see in the universe came to be, and we effectively are born out of one such fluctuation. So really, really important for the emergence of everything that's in the universe. And in the intervening 20-odd years, the precision with which we've been able to map out those fluctuations has gone up in a stunning fashion. That's 1994, the discovery of the fluctuations, another half of a Nobel Prize for Physics. 2004, 2015. You can see it's the same sky, but the resolution is getting better and better. And now this is essentially a Gaussian random field on the sky, and we've got very good physical reasons to believe that the distribution of fluctuations is very Gaussian. Indeed, departure from Gaussianity have not been discovered. And therefore, we can analyze this using statistical tools. And the first thing that you want to do with something like this, whose statistics distribution is known, is to do a Fourier analysis, effectively. So you can expand this temperature field in the direction in the sky in terms of spherical harmonics, such as the Fourier transform on the sphere. And then you want to look at the correlation function. You want to ask the question, what is the probability of finding a certain temperature fluctuation in this direction if I have a temperature fluctuation in that direction, and average all over the sky. And effectively, what you end up with is a quantity that we call the angular power spectrum, which is for the experts, is the expected variance on the sky. And for a Gaussian random field, this contains the full statistical information. So you can take this map, massage it into a power spectrum that contains all information that these fluctuations give. Not only that, we have very precise and very well-developed physical models that, based on Einstein general relativity, dark matter, dark energy, and the inflationary theory of the universe, give very accurate predictions for what this angular power spectrum should look like. So we can make very accurate fits to the data. And this is what it currently looks like. The data are in blue, and in red, you see the prediction of a 6-parameter model with the 6 parameters fit to the data. And you can see it's an extraordinary fit. You see the residual down here. This is light that has been traveling for 13.7 billion years through the universe. It's been generated 380,000 years after the Big Bang, and it's ultimately been generated by quantum fluctuations that we understand through quantum mechanics 10 to the minus 32 seconds after the Big Bang. And our model fits it perfectly. It's pretty impressive. I dare say this is one of the greatest achievements of modern cosmology, but it's also one of the greatest challenges, because in order to fit those data with this kind of accuracy, you need two components, additionally to the ones that we know about, dark matter and dark energy. Otherwise, it simply doesn't work. You wouldn't get this fit at all. We can look at other things in the sky. We can look at the galaxy distribution in the sky. In the 1950s, we only knew of a handful of other extragalactic objects apart from the Milky Way. In 1982, when people were still looking at photographic plates, this was the state of the art. 1,100 galaxies mapped out in the local universe. In 2013, this is what it looks like. 1.5 million galaxies mapped out by a dedicated telescope, the 2.4 meters Long Digital Sky Survey telescope on Apache Point in Arizona. And the point is that our increase in the data flow has been dramatic in the last 20 years. And so Rutherford, Nobel Prize winner, discovery of the atomic structure of the nucleus, was reported to be saying that if you need statistics, you should have done a better experiment, because simply your data were not good enough. But I hope you have convinced you that nowadays, if you work in astrophysics and cosmology, if you don't need statistics, then you're not working on the right experiment. Because it means that you're not at the forefront of what the interesting data-driven and model-driven problems are in the field. In order to work in astrostatistics, in cosmology today with data, you need statistics even just to start formulating the problem that you're looking into. And so astrostatistics can be formulated as being the development and application of advanced statistical methods to problems in astrophysics and cosmology, particularly in cosmology insofar as I'm concerned. That's my research interest. And so the idea being that we want to gather all of these different complex, complicated, but physically well understood data sets, ranging from the relic radiation from the Big Bang, stellar explosions in distant galaxies, the distribution of galaxies in the sky, numerical simulations of what the dark matter universe looked like, condense them down in meaningful statistical measure, explore the parameter space of these models, or the physical models that we've come up with using techniques such as Markov-Chain, Monte Carlo, and others, and ultimately boil it down to a set of numbers that we call the cosmological parameters that we need to measure, that are not known from first principle, but need to be measured essentially observationally. And while I won't go into the details of what those numbers are, those are the numbers that cosmologists are interested in. I want you to look at the error bars, which are nowadays sub-percent, really. And there's one here that's really interesting and meaningful. It's the age of the universe. 13,796,000,000 years, give or take 29 million years, which, is not much. It's a 0.3% error, right? We don't know the age of the Earth to that accuracy, and we sit on it, and we can tell, this is the age of the universe with this kind of accuracy. I should say precision to this audience. So I was in a session this morning, a very interesting session on data analytics for business, and I learned that in a conference such as this, you can't give a talk on data analysis and statistics without using a Venn diagram. So I tried to come up with my own Venn diagram to describe what astrostatistics should be like. But then I realized I can generalize this to X statistics, where X is anything you care about, astro, bio, econo, whatever statistics. And what you need is expertise in X, whatever X is. You need statistics, and you need coding. And that is, the intersection of these three is X statistics, whatever X is. But then I realized, actually, for astro, if X is astro, then yes, you need astro expertise, you need statistics, but the third important, I dare say, fundamental component is a different one. And that gives you astrostatistics. Now, astrostatistics really has taken off because of this simple fact. As a function of time, the number of stellar explosions called supernovae type 1a, I'm going to tell you a bit more about them in a minute, on a logarithmic scale. And you can see that up until the 1990s, we were in the few hundreds per year. But something interesting happens in the 1990s, of course, as we all know, CCD cameras and the widespread adoption of computers. And look at the jump. over an order of magnitude. And indeed, 10 years later, that's when the data came in that led to the discovery that the universe is accelerating. And the rate is continuing on a logarithmic scale. We're now climbing up orders of magnitude in terms of the data flow. Exoplanet, even more dramatic. This is not cosmology per se, but a hugely exciting frontier of research, the discovery of planets going around other stars but the sun. The first exoplanet was discovered in 1995, and this is when the Kepler satellite was launched, and the rise has been stunning. Nowadays, it used to be big news, new planet discovered, and nowadays, people discover hundreds of planets at a time, and it just barely makes the news nowadays because we've got so many exoplanets discovered. And this is the new normal. Indeed, this is an overview of the entirety of the data that we have about the universe, a project that I put together in collaboration with the Data Science Institute and some of my students. And I've tried to come up with a way of visualizing everything we've measured about the universe. So to my knowledge, this is the most complete map of the universe ever produced. And what it shows is the position on one of the two coordinates in the sky for the object versus distance measured in Earth radii. So this is low Earth orbit. You see the satellites here. You see the geostationary satellites. You see the planets and the moon. You see here the asteroid belt between Mars and Jupiter in the solar system, the Kuiper belt at the end of the solar system. Up here, that's the furthest object mankind has launched, Voyager 1, which was launched in 1977. It's now making its way beyond the edge of the solar system into the so-called heliopause. But now let's move up 9 orders of magnitude in distance to the galactic domain. And here there is a big place of nothingness, nothing, 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 until here, those are Milky Way stars, mapped out by the Gaia satellite. The red dots are exoplanets, the confirmed exoplanets. That's where the Milky Way ends, and that's really where the dark matter halo encompassing our Milky Way ends. But if you want to go to cosmology, you need another 6 order of magnitude up. And this is cosmology. Each dot here is a galaxy. Each one's got about a few hundred billion stars in it. And at the very end here, there are quasars, even higher energy emission of light and energy. And at the top here, the microwave background, the end of the visual universe. So if you compare our map with the original map that was produced by Gott et al. In 2005, you can see that on all scales, the increase in data sets has been dramatic, be it solar system science, be it Milky Way science, be it cosmology. So the increase is dramatic. So I think you're convinced, at least I've tried to convince you that we've got big data. And so you might say, so what? Everybody's got big data nowadays. I don't need to go to cosmology to have big data. But the point about astrostatistics is that our big data are special. Our big data are expensive but worthless. And that's very important, because each one of those data sets cost about $1 billion, pounds, euros, whatever currency you want to put on it. In any case, the pound now is going towards equality to any of them in any case. But they're free. The major funding agencies mandate that those data sets are made publicly available after a proprietary period that can be as short as 1 year. Which means that anybody can download the entire data set and all the scripts and all the codes that go with it and play with it at will. And that has been the driver for innovation, the driver for people with bright ideas coming in, doing new things that the team themselves that had gotten the data in the first place didn't dream of doing. And so this has worked exceptionally well for our field because there's no commercial interest. Those data are used to answer some of the most fundamental questions of humankind, but are of absolutely no commercial value, because nobody cares where a quasar is at redshift 7, except we do. Also, we got detailed physical models that describe the underlying physics. So it's not just all phenomenology, it's not all data-driven, it's also model-driven. And sophisticated modeling of the measurement process and measurement errors. So this has worked exceptionally well for some of the collaborations, the Sloan collaboration, WMAP, microwave background, Planck collaboration. Look at the number of citations that the papers have gathered in the last few years. I mean, so it's big science that's having big impacts. Also special about astrostatistics is that it's an observational science. We don't make experiments. We only make observations. We can't reproduce the universe at will, except in simulations. And also, interestingly, the box's quip about all models are wrong, but some are useful, doesn't really apply to us because we are physicists and we believe that we have right models somewhere there to be discovered. Our models are right. And if the data don't comply, well, it's a problem with the data, obviously. Interestingly, sometimes the sample size is 1. Some of the questions we ask are about the entire universe, for which we have a sample of precisely 1. And therefore, that throws up questions about fundamentals of statistics and probability theory. And that's one of the reasons why many of us are Bayesians at heart. And unless we are Bayesians, unless we wear our Bayesians on our sleeves, we are closeted Bayesian perhaps sometimes. But that's an ontological issue that comes up quite often in cosmology. And the astrostatistical landscape nowadays is really picking up. 600 papers a year, 100 a meeting a year, an active series of conferences, training schools, associations like International Statistics Association, of which the late Joe Hilby was president and was really his brainchild. Very active field of research to get into. And in fact, like I mentioned before, most of this is nowadays done with a Bayesian flavor. And if you compare the number of papers in astronomy, astrophysics that are Bayesian and are dedicated to methodological issues as a function of time, compare it to the number of objects being discovered, I think you can see a very clear correlation here, again, at the end of the 90s, the number of objects discovered picking up, as I described, the number of Bayesian papers following suit. And again, I believe this not to be just a correlation, I believe this to be causation, of course, that's my interpretation of this graph. Namely, the fact that astronomers faced with the data deluge, they had to find a way of making it work and to understand it. And Bayesian methods came to the fore for a variety of reasons. So really, the 2000s and the 21st century is the era of Bayesian astrostatistics. So let me now describe some of the problems that astrostatistics has been brought to bear on, in not a great amount of detail, but just to give you a flavor for the kind of questions, the science questions we ask and the statistics methods that we use. One of the most pressing questions, as I mentioned before, is that of determining the so-called cosmological parameters. Those are quantities that called omega something that describe what is the universe made of. So omega m stands for omega matter. Omega lambda stands for the cosmological constant dark energy. So that these numbers here that tell you how much matter there is in the universe in convenient units, so that if the content in matter in the universe is larger than 1, then the gravitational attraction of all that matter, be it visible or dark, is strong enough to overcome the Big Bang initial impulse, if you like, and eventually to make the universe recollapse at the end of time in the reverse motion version of the Big Bang, namely a big crunch. However, if this number is less than 1, then there isn't enough gravity to overcome the expansion, and the universe will continue expanding forever, albeit at an ever decelerating pace. So clearly you can see that determining this number is all important to determine observationally nothing less than the fate of the universe. This assumes, however, that the cosmological constant, or dark energy, if you prefer, is 0, which was the expectation of everybody until the late 90s when it was discovered this not to be the case. It turns out that if this new form of energy is actually positive, and if it's larger than the amount of matter, then it takes over, and the expansion of the universe does not decelerate in the future. Indeed, it accelerates, and the end of the universe looks rather different. It's so-called the big freeze, where everything flies away from everything else at an ever-accelerating pace. Galaxies move away from each other faster and faster, so fast indeed that light can no longer traverse the space between them, and everything, all the galaxies turn off, all the stars die, everything gets sucked in by black holes. Black holes eventually disappear, and everything is dead and cold, and that happens in the next 200 billion years or so. Now, incidentally, it's a very good reason why we need to do astronomy and astrophysics cosmology now, because if you wait 200 billion years, there won't be any more galaxies left to observe, so that's always a point worth making when you ask for money for funding. And so the picture that the astrostatistical analysis of a variety of data has led to is this rather strange cosmic ingredient picture where normal matter, the matter that you and I are made of, is only 5% of the total. Dark energy is ripping the universe apart, 70%, and cold dark matter is 25%. And so this leads to a model that we call lambda CDM for cosmological constant dark energy, CDM for cold dark matter. There's also photons and neutrinos out there, but they're really a small part of the total. And so one of the key ingredients in trying to determine those cosmological parameters is to understand how did the universe expand over cosmic times. So Einstein's general relativity leads to a simple differential equation for a quantity called A, which is the scale factor. It essentially is a function of time that tells you how fast the universe is expanding as a function of time. And you can see it's a differential equation which has got a bunch of free parameters, which are the cosmological parameters that we need to determine. And they're not determined from first principle. We just need to measure them from observation. There's no other way around. And so how do we go about doing that observationally, and what kind of statistics do we need? It turns out that there is a relatively conceptually simple way of doing that. So if you can measure the distance to objects in the universe, and you can measure redshift, which you can think of as the velocity at which those objects are moving away from us on this axis, it turns out that the relationship between distance on the vertical axis and velocity of recession on the x-axis depends on the cosmological parameters. And you see three different curves there giving you this relationship between distance and velocity as a function of what the choice of the different cosmological parameters are. And so if you can measure both, then you can determine statistically which one of this curve you're on and translate this into an understanding of what cosmological parameters you have. Hubble, in his measurement, was down here. You see everything here is linear, so there's only one parameter. But if you go to larger distances, larger velocities, then you can tell things apart. The problem is, funnily enough, with distance, we're really, really bad at determining distances in the universe because it's a hard problem. If you think about it, how would you know the distance to a star? You know, you look up in the sky and you see the sun is very bright, of course. And then you look up at the night sky and you see the top three brightest stars, and they look, a certain brightness. And you might think, well, actually, Sirius must be the closest one because it's the brightest one, right? But of course, they're not all of the same intrinsic brightness, and the apparent brightness is a combination of how bright they are intrinsically with how far away they are. The further away, the dimmer they become. And so if you put all of them at the same distance, then you'll find indeed that the sun is actually much dimmer than Canopus, which is 15,000 times brighter. Proxima Centauri, the nearest neighbor star, is only 1.5 times as bright as the sun, and Sirius is 25 times as brighter. But the point is that by only looking at them in the sky, you have no way of knowing how far away they are. So how do we go about measuring distances in the universe? Well, there are two ways. If you actually have a standard candle, if you know that the intrinsic luminosity of the object is fixed or known, and you measure the apparent flux luminosity or the luminosity in the sky, you can work out the distance using essentially the cosmological equivalent of the inverse square law. Or if you have an object whose size is known, and you look it up in the sky and see what angle it subtends, then using trigonometry, you can work out the distance to that object, and that's called angular diameter distance. Turns out that the two distances are not the same, so there are actually two different ways of defining distance in cosmology, but they're related by a simple relationship. So we can actually measure things out there if we know how intrinsically bright they are, or if we know how big they are to begin with. So that's very good, but now we need something bright, something that we can measure from very far away. And fortunately, there is a class of thermonuclear explosions called type 1a supernovae that fit that bill. So if you take a white dwarf, which is a very compact, very dense, very cool star, you put it in a binary system with a red giant such as this, and the white dwarf starts sucking in the red giant's gas, eventually the gravitational compression of the white dwarf is such that the runaway thermonuclear reaction is initiated, and the white dwarf explodes in a way that's almost standard. In other words, the amount of mass that's needed to make that star explode is essentially controlled only by gravity. And therefore, in exploding white dwarfs, we have a standard candle that we can use to signpost the expansion history of the universe and reconstruct the cosmological parameters. And so the way this is done in practice is by going out and measuring lots of galaxies and looking for an extra bright star in a cosmic spot the difference kind of game. Are you any good at doing this game? Can you see the extra bright star on the right-hand side? Here. So if you spotted it, you would have been a good PhD candidate in astronomy in the 1980s. Because that's how it was done. Nowadays, we don't need graduate students to do this boring job anymore because we got computers. And we can do things like taking pictures during the explosion, after the explosion, automatically subtracting them off and identifying candidates. And indeed, this is what these three guys have done in the late 90s. and won a Nobel Prize for doing it. And the evidence that the universe is accelerating is in this graph. The difference between this curve, which has got dark energy, and that curve, which doesn't. So by eye, it's not immediately clear that there is a significant difference there. Yeah, you can see this cloud of points being slightly higher up. It's about a 3 sigma significance, enough for a Nobel Prize. And nowadays, we put it all together, combining different data sets on the right-hand side graph, we end up with very precise constraints on the cosmological parameters, matter on the x-axis and cosmological constant or dark energy on the y-axis. Of course, we don't understand any of it in terms of physics, but the data are quite clear. Now, so that's one example of how we use statistics to infer cosmological parameters. Operationally, methodologically, most of this is done in a Bayesian way. And just to remind you, Bayes' rule is a really simple rule, essentially just a way of expressing the joint probability of two propositions using conditional probabilities and then doing this. So it's essentially the content of Bayes' paper in the 1800s. But the interesting thing is that when we take A, proposition A, we replace it with theta for the parameters of interest. We take proposition B and we replace it by the data, then we really get talking. This is Bayes' theorem in terms of the posterior distribution for the parameters of interest given the data equals to the likelihood, which is the distribution of the data given the parameters, times the prior. So for inference, all you need to know is that the posterior is proportional to the likelihood times the prior. And cosmologists nowadays are by and large Bayesians for a number of reasons, and you can see it here. As a function of time, the number of Bayesian papers in cosmology is rising very sharply. So normalized to 1980 levels, this is the number of papers in astrophysics. It doubles every 5 years, but the number of Bayesian papers in astrophysics doubles every 2.5 years. So if you project this into the future, doing some bit of very dodgy statistics, by 2042, all papers in astrophysics will be Bayesian. And there is very good reasons why we are, by and large, Bayesians, because it's a principled methodology. It gives you the quantity you're after, namely the posterior distribution for the parameters or the hypothesis of interest, rather than the probability of the data if the hypotheses were true. Well, actually, not even that. The probability of getting data as extreme, blah, blah. Let me not get onto the p-value business. It's philosophically attuned, where you have only one universe to observe, is scalable, is efficient, is easy to use, and it gives you a comprehensive inferential framework for a number of things that we want to do in cosmology. So one of the frontiers of this game is not only inference on the parameters, but inference on the models. I told you before that we have a slew of interesting physical models, and what we want to do is to be able to compare them in a principled fashion using Bayesian model comparison, which is usually framed in terms of the Bayesian evidence here, the normalizing constant in Bayes' theorem. I won't go through the details of the math, but just to say that if you manipulate this quantity here appropriately, you end up with the probability of the model given the data, which is arguably the quantity you're after, and you can construct posterior odds for the models that you're considering in terms of the ratio of the prior odds times the ratio of the evidences, these integrals here. And so this Bayes factor here tells you essentially what is the shift in your degree of belief in the two models once you've seen the data. Let me just briefly motivate why we're interested in doing this kind of calculation. Because I think, specifically in astronomy, it's a really interesting question that goes at the heart of what science is about. Popper famously said in his influential work on inference and induction, that science proceeds by falsifying null hypotheses, which is essentially what p-values do. That you set up a straw null hypothesis and you try to shut it down by finding a significant p-value. But E.T. Jaynes argued very persuasively that actually successful predictions in science ought to be rewarded. In other words, if a theory comes up with a prediction that is then that we then fail to falsify, our belief in that theory should increase, right? Because a prediction has been made that has been verified by the data. And indeed, Einstein has been reported as saying that everything should be as simple as possible, but not simpler. Occam's razor, the idea that simple explanations are better than complicated multi-parameter exotic models. And we have a beautiful historical example in astronomy of just that phenomenon, where in the beginning of the 20th century, Einstein made a prediction that the deflection angle brought about by the gravitational pull of the sun in the light coming from a distant star ought to be twice as big under its general relativity framework as it would be using Newton's theory of gravity. A testable prediction of a theory that had no free parameters against Newton's theory, again with no free parameters. And indeed, in 1919, 2 expeditions went here off the Africa and off Brazil to measure this angle. And if you do the calculation of the Bayesian probabilities, you'll find that the posterior odds are 5-to-1 for Einstein, based on the data that were gathered by Eddington in 1919. 5-to-1. This is not a very strong. It's not a very strong result, but even so, it was sufficient for Einstein to become, the scientific myth for newspapers all over the world to lead with titles such as "Lights all askew in the heavens," "Man of science more or less agog of results." Einstein theory triumph, stars not where they seemed or were calculated to be by Newton, but nobody need worry. So all of that can be understood using the principle of Bayesian model selection and Bayesian model comparison. Indeed, there are examples of that in cosmology. This is an example from my work where we've adopted this kind of framework to classify systematically a large number of competing physical theoretical models for the very initial moments in the life of the universe, the first 10 to the minus 32 seconds after the Big Bang. And there are many other examples that I could give you, and I'm happy to do so. I just want to conclude with a couple of final remarks in terms of where we're going and where the opportunities lies in the future, because this is the future in terms of data and science questions is truly staggering. This is the Large Synoptic Survey Telescope, due to begin operations in just a few years' time, producing 200,000 images of the full sky every year at the rate of 1.3 petabytes per year, requiring about 100 teraflops of computing power to process. Nobody can inspect, let alone understand, this amount of data. And when it becomes truly staggering is when the Square Kilometre Array Radio Telescope comes into operation, which is expected to produce 5 times global internet traffic per year worth of data, and require of order 100 petaflops computing power to analyze those data. Those are truly staggering data sets for which even trivial operations such as computing means become real science challenges, let alone, don't even think about inverting matrices for this kind of data sets. And so where we have gone really in the last few thousand years has been from a place where in prehistoric times all we had to observe the sky was our naked eye, and historically people have done that and recorded their observations in any way they could. Then it took Galileo and his groundbreaking observations with his own telescope, here are the moons of Jupiter, to open up a new enhanced perspective on the cosmos, to the point that at the beginning of this century we are now in a position to be able to image planets going around other stars. But going forward in 2020s, it's no longer feasible for humans to even inspect the data, even just to make sense of the data. We will need statistical methods and advanced computational algorithms. And so statistics actually becomes our most powerful eye onto the universe. And so there is plenty of interesting big science questions awaiting answers, which will come from a mixture of methods that are both data-driven and science-driven, such as supervised classification, machine learning, high-dimensional posterior sampling, model selection, hierarchical model, feature detection. There is more. This is just a flavor of the kind of things that astronomers will need to be doing in the next 10 or 20 years. And in conclusion, we are come to a place where our knowledge and indeed our capability of learning more about the universe is already now limited, not by the amount of data or indeed by the ingenuity of our models, it is limited by our capability of processing, analyzing, understanding the data. And so we truly are faced with astronomical data sets, big science questions, many unsolved statistical challenges, truly a golden age for astrostatistics. Thank you very much. Thank you.